You are watching darkScript, IT and InfoSec tutorials.
Hello and welcome back to darkScript. I am super excited to see you again. Thank you for joining. Yes, you too, that tiny little viewer out there who's got nothing better to do than learn IT on YouTube. You just knock yourself out. Anyway, I'm gonna do my best and try to publish shorter videos from now on because I just realized that the average person in 2024 literally has the attention span of a carrot. So I apologize in advance to anyone among you who likes to listen to my voice as they fall asleep. That being said, let's dive into our new topic. So today we're going to talk about a very important concept called ACL in short, or access control lists. And if you are involved in IT and security, I'm pretty sure you've heard this term many times. The short and acceptable definition of an ACL, if I really had to narrow and break it down, is a set of rules controlling network traffic. Let it sink for a second. A set of rules controlling network traffic. Okay? And those rules, which follow a very specific order on the network device, they have one role. They filter who and what can access or leave your network. That's pretty simple, right? It's like a watchdog that prevents unauthorized people from entering your house, assuming that your dog is not a typical carpet and is actually useful. Let's try to break it down even further, okay? So long story short, you have a home network, and in that network you host different resources. It can be data, devices, services, interfaces, videos of your dog. But the main idea here is that not everyone in your network should have access or equal access to those resources, unless you have one of those open border policies at home. So you've created separate subnets for different purposes in your household. You can say one of them is your IoT network for all your IoT devices, Raspberry Pi, smart TV, smart boiler, etc. And then there is a dedicated network for guests, for friends, for annoying siblings. And there is of course one for your kids and all the malware they download. And there is one for your grandma. And there is one for you and your work and your personal stuff. You following, yeah? But the rule of thumb here is that those networks are logically separated by default. It means your kids shouldn't mess up with your Raspberry Pi or your smart TV, and your grandma shouldn't accidentally establish a null session with the admin share on your server, and the guests shouldn't be able to access your personal data, and your work emails shouldn't be exposed to all the ransomware that your kids just downloaded when they clicked that link that said that they want a new iPhone. On the other hand, maybe your grandma does need to access some files outside of her network, which happen to be stored on your file server, where you keep all the pictures of your dog and your Trojans and stuff. And maybe you need to be able to access your kids' network for monitoring purposes. And perhaps you might want to grant your kids some limited access to the smart boiler on the IoT network to allow them to activate it before shower. Those exceptions do happen, we're all familiar with them. In this scenario, everything is explicitly denied between the networks. No subnet can communicate with another subnet, but sometimes you need to make some exceptions. You need to make some compromises. Those exceptions, just like the explicit deny, they come in the form of ACLs, or access rules, and it's very similar to how firewalls operate. And security-wise, this is perhaps the best approach. We call this the principle of least privilege. And this principle is made to ensure that users or systems or other network entities only have the minimal permissions required to perform their tasks. It's made to accomplish an ideal balance between security and productivity, because too much freedom would increase productivity but compromise security, whereas too much restriction would improve security but impact productivity. So instead of having an open border policy saying that the kids' network can access any resource on the IoT network, which is obviously a very bad practice, you can declare in your router's ACLs that your kids' subnet can access only the boiler, nothing else. So you explicitly state that subnet ABCD/24 can reach only host 1234/32. That's it. Another thing I wanted to mention regarding ACL terminology is that traditionally there are two types of ACLs in networking. There's standard ACLs, where control is based on IP address, usually source IP, and we have extended ACLs, where control is based on multiple criteria like IP, protocol, and port number. So if we had to translate our requirements into actual ACL instructions, using pseudocode for now, pseudo syntax, it would look like this. So the first rule is an explicit deny. We say block all traffic between all subnets unless the incoming packet meets a specific criterion or condition declared in a previous rule. So we type deny any, meaning deny any traffic from any address or subnet to any address or subnet of any protocol. Then, on top of that, we say, okay, grandma needs to access our Windows file server. So grandma's network needs to access a specific resource on the work network. So we have to say allow 192.168.40.0/24. That's grandma's subnet. That's the source subnet. And the destination would be 192.168.50, that's the work network, .5, that's my file server. And we're going to type SMB for the protocol, for the file server protocol. And next was you accessing the kids network from your work network. So here you could say allow 192.168.50.3, let's say my work laptop, and the destination would be 192.168.30, the kids network, .0/24, that's the entire kids subnet, and the protocol would be set to any protocol. So I'm granting myself full access to the kids network. And last was your kids accessing the boiler via a web interface. So we could say allow 192.168.30.0/24 for the kids network. And the destination would be the boiler itself. So 192.168.10 for the IoT network, .4 for the boiler. And the protocol would be HTTP. Then what happens when a packet reaches the router? It goes through all those rules top down, and if there is a match, the packet is routed to the appropriate network. But if there is no match, the deny all at the bottom of the ACL will eventually drop the packet and tell the client that the destination is unreachable. Makes sense, right? I'll try to simplify it for you with a quick packet tracer demo. So I've got PC1 and PC2, and we assume they're both on different networks, different subnets. PC1 is on the class C network, or the /24 network, and PC2 is on a class B, or a /16 network, as you can see. But before we continue, we spoke earlier about explicit deny at the very bottom of your ACL. So everything is blacklisted by default, and you as a network admin approve exceptions by whitelisting certain types of traffic. But in this scenario, in this very particular scenario, it's actually the other way around. Everything is allowed by default, and this is how most routers operate these days, unless you actually configure them correctly. So if you have two networks directly attached to the same router, they will be able to talk to each other by default. So if I ping my friend there from PC2 to PC1, you'll see that communication is indeed going through. And if I do the exact same thing from PC1 to PC2, we get practically the same results. Open border policy, remember? So now instead of whitelisting traffic, I'll actually blacklist it. I don't want PC1 and PC2 to communicate anymore. They're spending too much time online. So now I need to log into my router management interface and check if I have any access lists configured in the first place, which I clearly don't, as you can see on the screen now. So we're going to create a new access list, and we'll give it the number 101, and that usually indicates the order and priority of my rules. Then we'll deny all IP communications from host 192.168.110 to 172.16.0.10, and I'll also do it the other way around. We block communications both from PC1 to PC2 and from PC2 to PC1, right? Then I enter the interface configuration mode, the one that I will apply my ACL on, and the command is really straightforward. The entry is IP access group 101, and in stands for inbound traffic. I'm going to apply the exact same policy on my second interface, because remember, communication works in both directions. And now, if I try to ping PC2 from PC1, you'll notice that communication has been blocked successfully, and I'm getting a destination host unreachable message on my terminal. Ha! Serves you well. And same thing from PC2 to PC1. Good. Okay, let's try to conclude this session as quickly as possible, because your attention is clearly degrading and you want to go back to your TikTok and Instagram and stuff. So what did we learn today? Number one, human beings need ACLs all the time and everywhere, because you don't want your kids to mess with your Raspberry Pi, and you don't want grandma to catch a virus from your kids. Did you get a joke? Number two, with ACLs, you show people that you are the boss. You control what comes in and what goes out, and you're not some Kamala Harris with an open border policy. Number three, you really better not store sensitive information on your secret admin share, because Granny's watching. She's a hacker now. That's all for today. Hope you enjoyed. Please don't forget to like, share, and subscribe to the channel. This could really help me feed my imaginary kids and dog. So until the next time, stay connected, stay safe, and thank you again for watching.